Hello, I'm going to record this video to cover the probably the first two or three items on this slide. This week we're into some chemistry. Now, I want you to be afraid of the chemistry. Um, Biology is at the level we're doing it in terms of molecules and cells, and even then as you go up higher through different levels of organization, biology is ultimately some applied chemistry. The good news here is that really there are maybe a handful, 5 or 6 fundamental principles that once you've grasped, you'll use time and time and time again. So I'm going to try and go through those quite slowly here, and we're going to introduce those principles by looking at the structure of water and the properties of water. And we'll talk about then how water is a good solvent, but not a universal solvent. And that will introduce us to a discussion of concentrations. And if you do any biochemistry, and when you do chemistry, that's for sure, you'll need to talk about concentrations. And concentrations and understanding concentrations is important because it helps you understand the directions of reactions and a lot of other aspects about enzyme kinetics. We'll then turn our attention to looking at pH. We'll talk about acids and bases, and we'll finish up talking about biological buffering. That is how you control pH in a biological setting. So we're going to return to the start of the list here and talk about the structure of water. So before we get into looking at the molecule and talking about the relationship between the structure and the function of water molecules, I'm going to introduce two very, very important foundational principles. The first one is the principle of electronegativity, and the second one is the principle of polarity. So you get polarity in a molecule because of a molecule's shape and because of different electronegativities in the atoms. So we're going to start off by looking at just a simple water molecule as a way of introducing these two principles. Now these are two of the most important principles that we're going to talk about with the chemistry, and we will apply them over and over and over again. There's nothing crazy difficult about these principles. There are a few definitions you have to understand and commit to memory so you can use them quickly when you need them. So, as what we normally do at this point in class is I would ask you to draw me a water molecule. So just stop the video and draw what you think is a good representation of a water molecule, and then start the video back up again. Okay, so hopefully you drew something that looked like one of these representations. And there are different representations here. The one on the left that you see is called a ball and stick model. And that's kind of a good representation of a molecule. All the way over on the right is a different type of representation called a space-filling model. And this lets you see the relative amounts of space that each of the atoms in a water molecule would occupy. In the middle, we've got a couple of chemical representations of the water molecule. So a water molecule is simply H2O. That's 2 hydrogens, and each of the hydrogens is covalently bonded to an oxygen molecule. So we introduce here the notion of covalent bonding and valence. So these are two kind of underlying concepts you need to understand to get a real solid grasp on what it means for a molecule to be polar, or for that matter, non-polar. So atoms, like oxygen and hydrogen, are most stable when they have an outer shell of 8 electrons. Now, if that's confusing for you, that's understandable. So you need to spend a little time just looking at electron configuration in atoms. So if we look at a hydrogen atom, for example, a hydrogen atom has a nucleus composed of a single proton. That's it. That's all it is. Single proton. It's got a single positive charge on that proton. Orbiting around that proton, around the nucleus of the hydrogen atom, is a single electron. And that electron has a negative charge, a single negative charge. So when we think about a hydrogen atom, it has just one electron, negatively charged, orbiting a positively charged nucleus, a proton. And that makes that atom electrically neutral because the single negative charge balances out the single positive charge. Now a hydrogen atom is going to be more stable if rather than just having one electron, it has two. Oxygen is a little bit different. Oxygen has a central nucleus with some protons and some neutrons too, and then orbiting around that it has two shells of electrons. Now hydrogen only had one with just that lone electron. Oxygen has two shells. It has an inner shell, and that has two electrons. Then it has an outer shell, and it's got 6 electrons. Now oxygen is going to be most stable if that outer shell has 8 electrons, and that's called the octet rule. So atoms try to bond or associate with other atoms so that they complete their outer shells. Now hydrogen, its outer shell only takes 2 electrons, whereas oxygen takes 8. So if we have an oxygen molecule, it's going to try and bond with 2 hydrogen atoms. And when those bonds form, the oxygen shares that electron that's in hydrogen. So when it shares 2 hydrogens, it's getting an extra 2 electrons. Now it's not getting them in completely, it's sharing them with the hydrogen. So if oxygen has 6 outer shell electrons, and it shares 2 with 2 hydrogens, it now has 8. And if we think about the hydrogens, if each of the hydrogens is sharing an electron from the oxygen, the hydrogens now have 2 electrons in their outer shell, and everybody's stable. When those electrons get shared, a bond called a covalent bond forms. So a covalent bond is simply defined as a bond that involves the sharing of electrons between 2 atoms. And so when we make multiple bonds between atoms and we get multiple covalent bonds, we end up with molecules. So in this water molecule here, we've got 2 covalent bonds, and they're shown by solid lines. And you see them in this representation of the molecule here as well. It's exactly the same. Don't worry about these symbols. We're going to talk about them in a moment. So that's covalent bonding, a little bit about electrons and electronic organization in atoms. So when you look at this oxygen covalently bonded to these 2 hydrogens, what you see is the molecule is bent. It's going to become really important in a moment. So now we turn our attention to the principle of electronegativity. Atoms, generally speaking, have slightly different electronegativities from one another. So what is electronegativity? Electronegativity is just a measure of an atom's tendency to attract electrons. What does this mean? It means that if an oxygen covalently bonds with a hydrogen, that an oxygen, because of its higher electronegativity, is going to have a stronger tendency to pull the electrons towards it that it's sharing with hydrogen. So if we wanted to think about that in terms of what the electrons in this bond are doing, there are 2 electrons in this bond which are being shared between the oxygen and the hydrogen. And because oxygen is more electronegative, that means it pulls electrons towards it. Electrons in this bond here end up spending more time close to the oxygen than they do to the hydrogen. So remember, what's the charge on an electron? It's -1. And so that means if we are pulling some negative charges towards the oxygen ends up with a slight negative charge. And that's what we're showing with this little symbol here. So this symbol here means electronegative. So the oxygen is said to be electronegative. Now hydrogen, it doesn't necessarily care too much about the electrons that it's sharing with oxygen. It's said to be less electronegative, and you can think about that as more electropositive. And so because the electrons get pulled over towards the oxygen, and the oxygen becomes slightly negative. Now bear in mind, we're talking about slightly negative, we're not talking about complete negative, we're not talking about ions yet, we'll talk about ions later. Because the electrons get pulled towards the oxygen, the hydrogen becomes slightly positively charged. That's all we're talking about when we talk about electronegativity. So again, what is it? Electronegativity is simply the tendency of an atom to attract electrons. So think about it like this. I've got 2 Great Danes. Sometimes they'll come in if I'm recording videos. Eddie and Henry. So if Eddie and Henry are playing with a tug toy, they're close enough in terms of their strengths nobody gets the toy. They just tug on it. It's the infinite tug of war, if you like. That would be like if we gave two oxygen atoms the ability to form bonds, and that's what happens in molecular oxygen. It's just two double bonded oxygen atoms. So that's like Eddie and Henry pulling on the tug toy. Now, what about if we substitute out? Let's substitute out Eddie, who's my younger Great Dane, for one of my friends, Westies. I've got a friend who's got some Westies, and those are the little kind of white dogs. So Henry weighs 170 pounds, and one of my friends, Westies, maybe 14 pounds. Who wins the tug of war there? Well, Henry will. And so in that kind of analogy, Henry's going to be the oxygen, and the Westie would be the hydrogen. So the tendency of the atom to attract electrons is called electronegativity. So what happens when the electrons are pulled towards the oxygen? So what happens is we end up with a slightly negatively charged end of the molecule because the molecule is bent. So the two hydrogens here make this part of the molecule slightly positive and this part of the molecule slightly negative. So what we need to turn our attention to now is why does that matter? The consequence of this shape and of this difference in electronegativity is the molecule is polar. Not all molecules are polar. If I put two hydrogens together, for example, and make hydrogen gas, then that's not a polar molecule because each of those atoms has the same electronegativity. So you will have to remember the relative electronegativities. Now, you could memorize the actual numbers, which represent the measure of electronegativity. I wouldn't recommend you do that. It's a waste of time. Is what you need to remember is this. You need to remember the relative electronegativities of the atoms oxygen, nitrogen, carbon, and hydrogen. So what my slide is trying to show you here is that the electronegativity of oxygen is much, much greater than the electronegativity of nitrogen. So the O is much, much bigger than the N. Nitrogen is much more electronegative than carbon and then hydrogen. Now carbon and hydrogen, I put them about the same size here. They have roughly the same electronegativities. They're not identical, but they're close enough. So if you have a carbon hydrogen bonded to a, if you have a carbon covalently bonded to a hydrogen, neither one of those pulls on the electrons with any significantly greater strength. And so neither of them ends up negatively charged. They both just stay neutrally charged. So when we have a covalent bond between, let's say, an oxygen and a hydrogen, we call that a polar covalent bond. And when we see molecules with lots of polar covalent bonds, the molecule becomes polar. Now, water, it's got two bonds. They're both polar covalent bonds. So water is going to be polar because of its shape. Now, if we look at a molecule which only has carbon and hydrogen bonds, it's going to be completely non-polar. So you have to start to get an idea of whether a molecule will be polar or non-polar from understanding the different electronegativities of the atoms and the shape. Okay, so those are the things you have to look at. So in class, we would give you a handout at this point, and it would be a table of molecules. And in those molecules, you've got to decide whether the molecule is polar or non-polar, and you need to indicate why. So that's in Canvas. Download that, take a look at it, try and work out whether the molecule is polar or non-polar and why that might be. Now, the most important thing is that you can explain why you decide the molecule is polar or non-polar. So remember, you're looking at the atoms and their relative electronegativities, and you're looking at the shape of the molecule. Okay, so stop the video, have a go at that worksheet, and then start the video up again. Okay, so we're going to move on from electronegativity and polarity to our second foundational principle. When we have polar molecules can hydrogen bond. So if we consider two water molecules, if we put those water molecules close enough together, because we have an end of the molecule which is slightly negative and an end of the molecule which is slightly positive, there'll be a weak electrostatic interaction between the slightly negative part and the slightly positive part, and we call that a hydrogen bond. A hydrogen bond. So hydrogen bonding between water molecules. So if you've got a glass of water, I got my beaker of water here, and the liquid water in there, all of the water molecules in there that are jostling around are making and breaking hydrogen bonds very, very rapidly. These are really weak molecular interactions. They're very, very weak. And so just because of the heat in my office, those water molecules are forming and breaking hydrogen bonds all the time. Now, this hydrogen bonding between water molecules leads to water's really unique properties. Now, you probably think water is a really boring molecule, but it's the molecule of life, right? You are 70 to 80% water. Depending on your hydration, you're 70 to 80% water. So it is a molecule very, very fundamental to life on Earth. It's used for all kinds of things. If you didn't use water to dissolve solutes, then excreting urea would be incredibly painful. If you ever passed a kidney stone through a ureter, you know how uncomfortable that's going to be. Imagine excreting crystals of urea rather than liquid urine. That wouldn't be fun. Your eyeballs are lubricated with watery solutions. If you didn't have that water and it didn't have characteristics that allowed it to be a mild lubricant, your eyes would scratch around in their sockets. Again, not fun. Same thing in joints. If you couldn't dissolve nutrients in water, then you wouldn't be able to move nutrients around your body. If water wasn't polar and it couldn't hydrogen bond, ice would not form on the surface of ponds and lakes, and in some cases pieces of ocean, and life would struggle because of the huge swings in temperature that we would see. So all of the characteristics of water that you will see in your book and that we will talk about in the next couple of weeks come down to hydrogen bonding. If you don't understand electronegativity and polarity, take a break, go back, watch the video again, take a look in your book, and then come back and start the video when we're talking about hydrogen bonding. Okay, so here's what I was just trying to explain without an image. Here is a water molecule shown in a space filling diagram. We've got two hydrogens, we've got an oxygen. Remember the shape of the molecule and the fact that the oxygen is electronegative pulls the electrons towards the oxygen. So the covalent bond between the oxygen and the hydrogen, the electrons are pulled towards the oxygen. So that means this oxygen is slightly negative, and we say that that's electronegative. Now the hydrogen, because the negatively charged electrons are being pulled towards the oxygen, ends up slightly positive. And if you put opposite charges together, then they're going to pull, and you're going to get this weak intermolecular interaction called a hydrogen bond. So this water molecule here is making 1, 2, 3, 4. Water molecules can make a maximum of 4 hydrogen bonds. Hydrogen bonds are shown with this broken dotted line. Okay, not solid lines, that's covalent bonds, it's broken dotted line. So if you're ever drawing something, you need to show a hydrogen bond, broken dotted line. That's how that would be shown. If we drop the temperature of water all the way down to 0 degrees Celsius, the hydrogen bonds become very stable because there's no molecular motion in the water to break those interactions, and we get solid water. If we heat the water up, we're going to have a very high rate of breaking those hydrogen bonds, and water will evaporate from the surface in the form of vapor. So as we see transition between states, those transitions are dependent on whether the hydrogen bonds are breaking more frequently or are stabilizing. So think about this. This is going to be critically important. If I want to break these hydrogen bonds, I put heat in. When I put the heat in, the bonds break. The corollary of that is that when the bonds form, heat comes out. Okay? This is going to become an important principle when we talk about cellular respiration later in the semester, so we'll come back to that. Okay, who cares about this? Who cares about all this chemistry? Well, like I say, all the properties that water has come down to hydrogen bonding. Thermoregulation. You wouldn't cool yourself down by sweating if water couldn't hydrogen bond. Oceans would freeze from the bottom to the top if water couldn't hydrogen bond. And we've got evidence that suggests that life evolved deep in oceans around hydrothermal vents. If they froze solid, life would have had a very difficult time getting started down there. If water froze at the bottom of oceans and oceans froze solid, we wouldn't have stable environments. Because water hydrogen bonds, we get thermoregulation of the environment. Oceans can absorb huge amounts of sunlight, thermal radiant energy, before they change temperature. That means the oceans don't have huge temperature swings like you see in the desert. Desert doesn't have any water, huge temperature swings night to day. So I'm going to introduce now an additional foundational principle that we are going to revisit time and time again this semester. This one is very important. Structure determines function. I'm sitting here playing with my glasses, so we'll use my glasses. My glasses have got two lenses. They're shaped to help focus light appropriately on my eyeballs, which aren't the right shape. I have astigmatism. So the lenses structure dictates their function. My glasses have these two arms, and they help hook around my ears. Their structure determines their function. I'm pretty clumsy. They're nice and flexible, so when I sit on them, they don't break. Their structure determines their function. Take a look around you. Everything you look at, its structure determines its function. In biology, this arises from evolution. There are some exceptions to this. We have appendices. We don't entirely know what they're for, an appendix. So we don't know entirely what they're for. We think they may be involved in immune function, but you have a structure possibly with no function. Men have nipples. They ostensibly have no function. So you often find structures that are functionless, but they're often developmental or evolutionary artifacts. Everything we're going to look at, you should be thinking about how the structure determines the function, and we can apply this to water too. So I'm going to talk about how the structure of water leads to polarity, leads to hydrogen bonding, and leads to thermoregulation. Now in your book, there's going to be examples about thermoregulation, about water acting as a biological solvent, and I'll touch on that too, environmental stability, many more. There's a whole figure in your book, or you can often find these figures if you don't have the book that I use, which talk about the relationship between the structure and the function of water, the biological properties of water. So make sure you take a look at that. Okay, so I'm going to explain thermoregulation in the context of the structure-function relationship in water. Water has a high specific heat. What is specific heat? This is a physico-chemical term. What is specific heat? Specific heat is the amount of energy that a certain mass of substance can absorb before it changes temperature. So we're talking about absorption of heat energy. So for example, aluminium at the top here in the kind of silver font has a specific heat of 0.9 joules per gram. Gold has a specific heat of 0.129 joules per gram. Methane has a specific heat of 2.22 joules per gram. Look at water, 4.186 joules per gram. What does that mean? So what that means is that you have to put more heat energy into a gram of water to raise its temperature by 1 degree Celsius than you do for methane. And you have to put much more into water than you do into gold, and much more into aluminium. How can you relate to this to help it make sense? Think about an aluminium pan, and I'm going to use aluminium because I don't think any of us have got gold pans in our kitchens. Think about an aluminum pan, and you fill it with water. You fill it with the same amount of water as the mass of the pan. Let's say the pan weighs 1 kilo, and you fill the pan with a liter of water because that weighs a kilo, and you put it on the stove and you heat it up. Ignoring some other weird physics that might be going on here, the aluminium warms up before the water does. It's going to take the water much longer. You're going to have to put in much more heat to raise the temperature of the water the same as you raise the temperature of the aluminium. That's because water has a high specific heat. So what has that got to do with anything? Well, before we start looking at the biological relevance of that, just want to discriminate between heat and temperature. Heat is energy, temperature is a measure of that form of energy. So don't switch heat and temperature when you're talking about specific heat. So water has a very high specific heat. Remember, this means it can absorb a large amount of water, a large amount of energy before it changes temperature, more so than an equal amount of methane or gold or aluminium. And generally is what we find is that the denser something is, the less you have to heat it up. So, what difference between water and methane could account for the difference in specific heat? So I just want you to think about a methane molecule. And if you don't know what a methane molecule looks like, that's okay. Normally I would draw one and we'd talk about what a methane molecule is. And if you don't know what that looks like, just take a break a moment and look up in Google methane molecule and look for an image of a methane molecule, and you'll find it's a carbon and it's got 4 hydrogens arranged around it. Take a look at that and then think about the water molecule. What differences are there in the two molecules, methane and water, that account for the difference in specific heat? So think about it, take a look at the molecules, stop the video, and when you've taken a moment, start the video back up again. Okay, so if you look at a water molecule, what you'll see is it's polar. And if you look at a methane molecule, it's not. Okay, now if that doesn't make sense, think about the electronegativities of the atoms in the oxygen and the hydrogen in a water molecule, and then think about the carbon and hydrogen in methane. Think about the shapes of the molecule. Think about how you get polarity in the water, but not the methane. Okay, so how does that polarity that you see in water explain the difference in the specific heat when you compare methane and you compare water? That's what we have to answer. And it's going to come down to hydrogen bonding. So when you have water, liquid water, if you put heat into liquid water, the first thing that happens is the hydrogen bonds break. The hydrogen bonds break, the water molecules move faster, some of them probably evaporate, but the first thing that happens is the hydrogen bonds break. So the absorption of heat energy into water doesn't go into the molecules, it goes into the bonds and the bonds break. What about methane? When you heat methane up, there's no hydrogen bonding. There can't be because methane's polar. So what happens? The molecules go faster. There's no hydrogen bonds to break, so the molecules just start moving faster. Remember, really all that heat is kinetic energy in molecules that makes them move fast. Now the water molecules, they can't move fast to start with because they're kind of held together by hydrogen bonds. Now hydrogen bonds in methane, you heat the molecules up, they just move faster. The temperature goes up because there's more heat energy there. So that's how we explain the difference between specific heat in water and methane. Same thing for gold, aluminium, many other substances. Okay, who cares? What's the biological relevance here? The first biological relevance we can talk about is thermoregulation. So you are largely water, 70 to 80% of water. Now, when you sweat, you get a thin film of water on your skin. So what happens is the heat transfers from your skin into the water. Hydrogen bonds in the water between the water molecules break. The water molecules move faster. Some of them move fast enough to change state and become vapor. And the temperature of your skin has dropped because as water molecules leave, they're moving faster. They've taken heat with them. The heat has been used to break the bonds and allow the water molecules to leave. And so the surface of your skin, due to the transfer of heat energy from your skin to the water molecules and the breaking of the hydrogen bonds, leads to a lower temperature in the skin. That's how sweating works. If you didn't sweat water, you can thermoregulate. Neonates, babies, they don't sweat, but they're largely water. So they still thermoregulate just because they have a pretty high heat, specific heat. Okay, so there's two biologically relevant applications of understanding electronegativity, polarity, and hydrogen bonding. You can look in your book and you can see many, many more of these examples, and you should read through and apply your understanding of electronegativity, polarity, hydrogen bonding, for example, to how water moves through a plant, that kind of thing. Let's look at one last biologically relevant example here. I love this example. This is obviously a representation of our planet. It's all been stretched out. It doesn't look like this. The sizes roll off. It's totally wrong fundamentally. But it's what the map shows that we're interested in is the difference in temperature night to day. So the darker the color, let's look at Australia down here. The darker the color, the greater the temperature change from night to day. And we can look at Africa as well. Look at Africa. Okay, lots of desert here. Lots of desert here down in Australia. The high alpine deserts down here. Even if we look around up here where we live, we see some pretty dramatic changes night to day in the temperature. But let's keep a focus on these deserts down in Australia and in Africa. So what happens in the deserts is that noon comes, temperature's really high. Night comes, it gets really cold. Have you ever been in a desert? It gets cold at night. It gets wicked cold at night. In fact, there's water, it freezes. There's not much water because it's a desert. But yeah, these big swings in temperature. The lighter the color, the closer the temperatures are night to day. Where do you see the lightest colors? It's the oceans, right? It's the oceans or where you find lots and lots of water. So if you look around these coasts of Australia, down here particularly, you actually have rainforest. Rainforest. When you find rainforest, wherever you see lots of water, you tend to see very little difference in the temperature night to day. You also find in these places huge biodiversity. Life likes stability. These moist environments are very, very stable because the temperatures don't fluctuate wildly. So if you don't thermoregulate with the environment like a lizard might not do, and certain fish species don't necessarily thermoregulate particularly well, then you can't tolerate dramatic changes in temperature night to day. So we get thermoregulation of the planet because of the high specific heat of water. And that's why we see vast differences in diversity of habitats. Deserts and the organisms we see there are there because of these dramatic swings in temperature. Oceans, massive biodiversity, biggest biomasses on the planet in the oceans. So that's another nice application of biological relevance. At this point, I'd give you a handout and there'll be a bunch of questions on there for you to work on. And so there's a practice problem set you can download from Canvas. There'll be some multiple choice questions with some keys and then some short answer questions that require you to apply your understanding of electronegativity, polarity, hydrogen bonding to some biologically relevant examples. Okay, the last thing we're going to talk about here in the last few minutes, we're going to talk about the principle of dissolution. What does that mean? It means that water dissolves certain things, but not other stuff. You know this intuitive, right? Sugar, salt, they dissolve in water. We need to explain why. Other things, and this is just important, other molecules, oils, don't dissolve in water. Both of those things are important. A lot of people focus on the things that get dissolved and ignore the relevance of the things that don't get dissolved. So we'll talk a little bit about that and then we'll come back to this. So we need to explain how water can dissolve things. Who cares? Well, if you couldn't dissolve nutrients, you couldn't move them around your body. If fats dissolved, your membranes, which are lipids, would dissolve and you would be a gooey, blobby mess on the ground. So that's why we care about this stuff. Okay, so water is an excellent solvent. Some people say it's a universal solvent. I hate that. It's not a universal solvent. It's just a very good solvent. So what happens is when we put a molecule or an ion in water that can dissolve, is what happens when something dissolves is that the water molecules arrange themselves around the molecule, either because the molecule is polar or because the molecule is charged. So what we're looking at here is a crystal of sodium chloride, and it's being dissolved in the water. So the green dot here is a chlorine ion. And so you can see that the water molecules around it are all surrounding the chlorine by pointing their slightly positively charged hydrogens towards the negatively charged chlorine. That is dissolving something. When it's surrounded by water molecules, it's dissolved. Don't confuse dissolving with the breaking of bonds, okay? That's a big mistake to make. We'll talk about it lots more as we move through the semester. Now this sodium ion here is positively charged, and so these negatively charged, slightly negatively charged oxygens surround the positively charged sodium, and it's dissolved. So that's how things get dissolved. Other things, I mean, methane. Let's think about methane. Can you dissolve methane in water? What do you think? You can't, right? Because it's not polar. So by understanding about the shapes of molecules and about electronegativity and about what hydrogen bonding is, you can pretty quickly start to work out what dissolves and what doesn't dissolve, and that's going to be important for our course. So here we've got butter, for example. Butter doesn't dissolve in water. Why not? Because butter is stearic acid. It's a fat. It's just carbon and hydrogen with a tiny little bit of oxygen, but it's primarily carbon and hydrogen. Doesn't matter how you arrange the carbon and hydrogens, right? You can't make butter polar. You can't make stearic acid polar. So that's why not all molecules would dissolve. And so your membranes are largely made of molecules called phospholipids, and they are made primarily from fatty acids. And so you don't want your membranes dissolving, because then you would dissolve and you would just be a blob on the floor, no puddle. That'd be bad. Okay, next time we're going to look at concentration, how you calculate concentrations. We'll look at how you concentrate molarity. We'll also talk about pH and buffering. Okay, so that's what we'll talk about next time. That's it. I'm going to get this uploading into YouTube so I can post it for you all. And I will see you on Wednesday when hopefully we have less snow.